Finding a person's phone number in a completely randomized directory is a physical impossibility. Without structure, you're looking at an avalanche of data. For a human to find anything efficiently, that list must be sorted. Otherwise, we are forced into the slow, manual labor of searching line by line and page by page. Computers face the exact same problem. Digital information isn't just an abstract idea. It's millions of ones and zeros physically trapped inside hardware. To make that information useful, it must be organized. But moving those physical bits into the correct order requires an intense mechanical process. The most intuitive way to solve this exact problem is an algorithm that actually mimics human behavior. It's called bubble sort. The core mechanic is simple. Compare two adjacent items and swap them if the larger one is on the left. Then move one step right and repeat. Step by step, the largest item visually bubbles to the end of the line. For a tiny data set on a desk, this method is elegant. It's easy to understand and requires almost no complex logic to execute. But this raises a paradox. If this algorithm is so effective for a few items, why do modern computer scientists avoid using it at all costs? The issue is that a computer lacks an aerial view. While you can look at a whole row of data at once, the machine cannot. Because computers store data in memory arrays, the processor can only see the two specific, contiguous slots it is currently comparing. This tunnel vision has a mechanical consequence. To ensure no items are left out of order, the computer must make redundant passes over the entire dataset. Achieving a perfect sort requires roughly n full passes over n total items. By attempting to solve a massive, global problem using only narrow, localized information, the machine generates an immense amount of wasted effort. The total workload is defined by a specific formula. The total number of steps is roughly the number of items squared divided by 2. For a set of 8 items, the result is 28 mechanical steps. A modern processor handles 28 steps in a fraction of a millisecond. You wouldn't even notice it happening. But look at what happens when the scale shifts from 8 items to 1 million. At 1 million items, the computer is suddenly forced to execute roughly 500 billion operations. This is what computer scientists call big O of n squared. It is the mathematical definition of a scaling trap. For early computers, like the Quadratic mainframe, processing cycles were precious. Running an n-squared algorithm on a large dataset could take hours or even days. Bubble sort self-destructs against the reality of scale. The more data you give it, the more the math works against the machine. This raises a question of design. If the scaling is so poor, why was this algorithm ever used by the pioneers of computing? The reason lies in the hardware. In the early era of computing, physical memory was more limited than time. Bubble sort sorts data in place. It requires 0 additional memory beyond the original list. This is an algorithm built for frugality. It pays a massive tax in time to preserve every single byte of physical space. Modern alternatives like merge sort are designed specifically to bypass the n-squared trap. Merge sort cuts the processing time down to a fraction of the original by repeatedly dividing the data in half. However, this speed has a price. Merge sort requires double the physical memory to temporarily hold those divided halves. You can have the extreme frugality of the slow approach or the lightning speed of the greedy approach. This highlights the core reality of computer architecture. There are no perfect solutions, only trade-offs. To buy speed, you must almost always spend space.